This video focuses on lesson 1.1.3, Navigation. In this lesson, we will review the history of navigation and learn about the different navigation methods aircraft use today. Let's begin with some navigation history. First, let's take a look at maps. Now, we all have an idea of what maps are. This is where objects are plotted on paper to represent the Earth's surface as seen from above. We use imaginary lines, known as latitude and longitude, to make a grid to describe where something is located. Latitude lines run east and west and measure north and south, and longitude lines run north and south and measure east and west. The next part of navigation history that we are going to look at is ocean passage. Now, originally, sailors would use time and velocity, known as dead reckoning, in order to be able to cross the ocean. Now, there's some debate about where the term dead reckoning comes from. Some claim that it is of Portuguese origin and that it was originally deduced reckoning because they would use time and velocity to reckon where they were going. There are other people who say that it means that if the reckoning is done incorrectly, you will probably end up dead. And there are others who claim that it simply refers to accuracy, like in the phrase dead center. So there is a great debate over where the term dead reckoning comes from. Now, moving on from just using time and velocity, we then began to use sextants, which are tools that we can use to measure the angular altitude of a star above the horizon. Sailors could use this in combination with star charts to be able to map their path as they were crossing the ocean. And in addition to this, sailors also created walker logs, which were dragged behind the boat to indicate speed and knots. So that is a length of rope that has knots tied in it at certain increments. And as the rope would drag out, that would indicate how many nautical miles per hour the boat was traveling. Then when we started moving into air flight, early pilots often navigated by sight, and they would use a route that was set up by a chain of visual towers. Now, this required a line of sight from the aircraft to the tower, so if there were any clouds or haze or dust that would obscure the vision, a pilot could very easily get off course. If you look at the images on this slide, you'll see there was a chain of towers that were actually set up from New York to San Francisco, and they looked a little bit like the smaller image on the right. So then we began to use radio navigation, and there are a whole lot of radio navigation evolution pieces on their own. So the types that we're going to briefly cover include Loran C, which is long-range navigation, NDB, which is non-directional beacons, ILS, which is the instrument landing system, VOR, which is the very high-frequency omnidirectional range, and GPS, the global positioning system. So first, let's take a look at Loran. So again, Loran is long-range navigation. Loran C is actually no longer used. It was originally designed for maritime navigation and was a supplement to aerial navigation. Next, we have NDB, or non-directional beacons. Non-directional beacons measure clockwise angles between the airplane longitudinal direction, the direction the airplane's pointing, and the NDB. This is the oldest electronic navigation that's still used, and it can be used at a lower altitude than VOR. And the aircraft instrument that is used for this is the Automatic Direction Finder, or ADF. So now let's talk about GPS, or the Global Positioning System. So this is a US space-based radio navigation system, and it provides three-dimensional locations: latitude, longitude, and altitude plus time. The components that go into GPS are satellites orbiting the Earth, and then the controlling and monitoring stations on Earth, and then the GPS receivers that are owned by users. Now, there are some aircraft that have GPS. In fact, a lot of aircraft do. The difference is that a pilot can see GPS inside of the aircraft, but air traffic control actually is still mostly radar-based. So we still need to use our radar-based navigation systems in order to communicate with air traffic control. That is being slowly updated, but at this time, that is the current system. So then we have the instrument landing system, and this is the navigation aid to guide the aircraft to the runway. The background image here, you can partially see some of those items, and we're going to take a closer look at those. So here we have the instrument landing system. So what you'll see is an outer compass, which is located right here. That outer compass is the first indicator as a plane is coming to the runway. They then move to the middle marker, and this is all measured by the glide slope transmitter. We also have a localizer transmitter and approach lights that are all part of the ILS. So the ILS aligns aircraft along the runway's extended center line. And that's an angle when it's viewed from above. And this aligns the aircraft on proper glide slope, which is the angled view from the side. So you'll see here that the plane is maintaining a steady altitude until it gets to right here. So this is our outer marker. And then once it comes in and it gets to the middle marker, it can either completely finish descending, or the middle marker is the final point that a plane could pull back up and begin circling again if it needed to. And here we have an image of an ILS instrument. You can see we have some different components here, and that it has some compass markers. We have north, east, west, and south, as well as degrees on this instrument. So here, what this graphic is just showing you is the different instrumentations that occur depending on the angle of attack coming into the runway. So this is your glide slope indication. Okay, and then this is your localizer indication. So this is what the instruments look like when we are looking at the direction from the above point of view. So as you can see, plane B is coming in directly straight. So those indicators look like these right here. If you look at the difference with plane A, which is coming in at a more drastic angle, you'll notice that this has an angle to it, and this yellow bar is actually pulled to the right a bit. The opposite angle does the opposite. The yellow bar moves to the left, and then we have the opposite angle in the instrumentation. So the ground equipment for the ILS looks like this. We have the glide slope antenna right here, and then we have the localizer center line antenna. So if you've ever looked at a plane while you're taxiing on a runway, you may have seen some of this equipment on the ground. So now we're going to take a look at an ILS approach plate. This plate example gives us a lot of information about how the plane comes in. The part that I want to point out, though, is actually this box right here. So what this is telling us is that if you were approaching this runway, a plane should maintain 2700 until the outer marker right here. That's indicated. And then they should have a normal descent at 182 degrees until or down to the middle marker. Okay, so now we're going to move into VOR. So VOR stands for Very High Frequency Omnidirectional Range, and this shows an aircraft position relative to a VOR radial, which is on the ground. And this is actually very commonly used in aircraft. This is the one thing that air traffic control does relay through signaling. So this is why we do have GPS in planes, but again, the pilot sees the GPS indicator on a map. It's not relayed to air traffic control. So VOR uses a magnetic north as the basis for all of its navigation, and it is the only reference direction is determined with the vacuum system. So magnetic north is accurate during an electrical failure, which is another bonus to VOR. So let's take a look at an analogy. So let's say that let's say you can imagine a constant rate of a rotating light beacon. So picture a lighthouse. And it is rotating in all directions, so it's omnidirectional, and it strobes every time it points north. So let's say that the face of the lighthouse goes into the ocean, it circles, and the light flashes every time it faces the ocean, which is north. The delay between the strobe flash and the sweeping beacon is the number of degrees from north at which you're located. So the amount of time it would take for you to see the flash of light again from the rotating light is the amount that is the degrees from north at which you are located. So let's take a look at some radials. So a VOR transmitter on the ground looks like this. These are typically at the very ends of runway, so you don't normally see them if you're in a plane. You might see them if you're landing, if you're able to see the ground, but most of the time, you're not looking out the window. So, at least I'm not. So VOR radials transmit direction information, and that is in these degrees. So obviously you see the large degree markers, 360, 90, 180, and 270. But in between there, we have these smaller branches that indicate smaller amounts of degrees. And all of these are based off of the degree from north. So radial is a specific beam that's transmitted to a VOR station. And then we have 360 radials, 1 per degree. So accurate navigation can actually be up to 1 degree of precision, and radials are named based on a clockwise bearing from magnetic north. So a 90 degree radial points to magnetic east from the VOR station. So 360 is always north, and then 90 is always going to be east. And VOR is effective at about 1,000 feet above ground level, or AGL. So let's look at some benefits and limitations of VOR. So the benefits are that we can have multiple stations, so multiple cross checks. We can essentially triangulate between different areas to determine our position. And we have very little interference from lightning or other natural issues. And it also allows us to have straight line courses. This also can allow us to automatically adjust with wind drift. And it does work regardless of the aircraft's orientation. Now, some limitations that we have are that they are ground-based transmitters and that we do need a line of sight for the frequencies. We also have a limited range when we're at lower altitude and at higher altitude. It's not really a global solution. So let's look at some sectional chart symbols. So VOR, in order to calculate where you're at, you use something called a sectional chart. This is essentially your key for those charts. So the shape right here is the VHF omni range of VOR. So VOR is co-situated with a technical air navigation, or can be. And then we have our vortex, which are right here, and then our Vor Dme, which is our distance measuring equipment. So here we have an actual VOR map. This looks really intense, and it's much easier if you zoom in on them. We'll be taking a much closer look at several of these in class, but right here you'll see that we have a Vor Dme right here based in that, okay? And that then has this circle around it. So you'll see this is the center, and then we have this circle around it. That is indicating those degrees that we talked about earlier. And then the VOR has a blue color compass rose showing its magnetic direction that the radials are transmitted in. So you'll see the compass rose right there. Okay, so this is another example of a VOR sectional chart. This one, it's really easy to see the radials around the edges. So here you'll see it starts at 0 and then it rotates clockwise, so you get a really good view. So again, this is just an example to show you some more of the dynamics of a VOR in the area. It's also indicating the compass rose. They are indicated in blue. Now, I know some of you are going to see Arlington and think this is a local map. It actually is not. You'll notice up here, there's a little bit of Wisconsin in the corner. Okay, so let's take a look at the VOR airborne equipment. So the VOR instruments operate when tuned to a station frequency, and typically it's tuned to 2 different VOR stations for cross-checking. Most general aviation aircraft have 2 VOR receivers, nav1 and nav2, inside of the cockpit. So this is what that equipment looks like. This is what goes inside of what we refer to as our 6-pack, which is our navigational panel. We'll be talking more about the 6-pack in our upcoming lessons. So if we look a little bit more closely at our instrument components, here we have the transceiver and then we have the VOR receiver. We have the volume control or indent, that's over here. The switch standby and the active frequency is here, and then our frequency selector is right here. And this is how we tune into different VOR stations that are on the ground. And then we have the actual indicator right here. So this indicates our heading. Then we have our selected course slightly below that. We do have a warning flag that if we get too off course, this is our glide slope indicator. This is our to and from indicator. So it's letting us know where we are in relation to the beacon that's on the ground. And then we have our reciprocal of the selected course, which is obviously backwards. The omni bearing selector. Again, we have a glide slope warning flag, and then we have a course deviation indicator. So this area is what changes if we are off course. And all of that correlates to this. So what we're looking at is if this is our VOR, okay, then what happens is the sky gets divided into to and from, as well as left and right of the station. So what we do is this is currently tuned to, so we're saying that this is tuned to the 90-degree radial. And so right now we are looking at the fact that we are a little bit off course based upon the radials over here if we are tuned to that 90-degree. Okay, so what we're looking at with our course deviation indicator is that it indicates the angular deviation of the aircraft position relative to the radial. So that's how far we are off from an angle. Now remember, our goal is always to have a straight path. Okay, so the greater CDI deflection means a greater angle that we are away. So we have this guy right here, and you'll see that this aircraft, if this is our ideal angle, okay, and this is the VOR, so if this is our ideal angle and this is where our aircraft is, we're 305 versus the 300. And this is more minor right in here in terms of this white piece telling us how far off we are from angle. This plane is further off, so therefore that angle is more severe. So this CDI indicates that you're on the selected course. This is indicating that you're actually 4 degrees right of your selected course because that is going to the left. So here are some more examples. If we're looking here, none of these are actually on course because that white bar would be up and down. Right now, in this one, we are to the left of our VOR because that angle went to the right. This one, we are to the right because it points to the left, but it's in the from direction or the to direction. So we are moving away from the VOR station, and here we're moving to the VOR station. So here's some more examples. I'm going to pause here and give you guys some time to just look at these. I'm going to put a counter up, and I'll give you 30 seconds to, based on what you know, look at the aircraft that are in this image and the dials over here and trying to figure out which aircraft matches which. We'll talk about this more in class. So here are some more examples. We have some aircraft and we're looking at it from a different perspective. And so we have the indications over here and our aircraft here. I'm going to pause again and give you a few moments to analyze which one matches which aircraft. Okay, so this is another VOR instrument example. Okay, so to determine the present direction from a VOR station, we have to tune into the station with the OBS knob until the CDI needle indicates or centers with a from direction. So we're rotating that knob until we have a centered from direction. And then to determine the course from your present position to a VOR station, we can turn that knob until we center with a to indication. So when the CDI begins to center, you turn right and track inbound to the station. So then you can set up an intercept angle by turning left to a heading of 45 degrees. Once you establish your intercept course, you turn the OBS to set the new inbound course of 90 degrees in the VOR indicator. So then you can track your inbound on the 250 degree radial and then you see the cumulus clouds and decide to go to 270. So what this is showing you is that if we start here, okay, we are trying to get to our VOR, so we have to come across here and do a little bit of a change in order to get around that cloud cover. Okay, so now I'm going to ask you to look at the graphic to the left, and I want you to reflect on how the information from the VOR is being used to navigate the aircraft. Okay, so the last thing we need to look at is our distance measuring equipment, and this measures the slant range. And the error increases as you approach the DME, so it gets less accurate the closer you get. So in this graphic, you can see that our slant range mileage is approximately 10 nautical miles. And that is because we are about 6,000 above ground level. Okay, and so that slant range is 10 nautical miles because we were just solving for the hypotenuse of this triangle. Okay, so here's another example of DME slant range. So here we have our DME. We have 1 nautical mile, and we are up 1 nautical mile, which gives us a slant range of 1.4 nautical miles. Okay, so that wraps up this presentation. We'll be taking a closer look at all of these in class and doing a lot of practice. So if you have any questions or you're a little bit confused, jot them down in your notebook and we will talk about them when I see you in class.